Hey everyone, welcome to This Explainer. Today, we're doing a deep dive into the chapter on searching from our source material. And honestly, this is all about the invisible logic that powers literally every single search you do on your devices. Think about it. Every time you hit find on a web page, or pull up a contact on your phone, or search a massive database, there is an intricate dance of computational logic happening in the absolute blink of an eye. We're going to unpack exactly how that works today. Look at this quote by Brian Kernighan. He really hits the nail on the head here, explaining why understanding these algorithms matters to all of us. You really don't need to be a software engineer writing lines of Python to get something out of this. We live in a deeply digital world, right? So understanding how data is actually retrieved just kind of demystifies the tech we rely on every single second. It takes computers from being these magical, mysterious black boxes to logical, totally understandable machines. To get there, we'll be tracing the evolution of computational efficiency. Here's our quick agenda. We'll start with the problem of searching, then look at linear search, binary search, hashing, and finally, collisions. Let's get into it. All right, part one, the problem of searching or locating elements. Let's think about a problem we all deal with, finding something we've lost. Think about your own home for a second. Sometimes you know exactly where something is. Like your favorite coffee mug is in the left cupboard. You just go and grab it. Easy. But what if you misplaced your car keys? You don't know the exact location, so you have to physically search, right? You're basically looking room by room, exhaustively. Well, a computer does the exact same thing. It stores massive amounts of data, and searching simply means locating one particular element hidden inside that huge collection. So our first stop on this journey is the most fundamental method out there. Part two, linear search, which is all about exhaustive checking. The crucial thing to remember here is that a linear search is exactly like checking every single item in your house, one by one, until you finally find those keys. It's literally the absolute simplest way to search. The computer takes the item it's looking for, we usually call this the key, and just compares it sequentially. It looks at the first item, then the second, then the third, and so on. It only stops when it gets a match, or if it hits the very end of the list and realizes, nope, it's not here. Let's actually see this in action. Imagine our computer has this totally unsorted list of numbers. If we want to find our key, let's go with the number 17, the computer starts right at index 0. Is 8 equal to 17? Nope. It moves to index 1. Is -4 equal to 17? No. It has to do the tedious work of checking every single number sequentially. Finally, at index 3, boom, it hits a match and stops. But wait, here is the massive catch with linear search. Think about the variable n, which just stands for the total number of items in a list. What if the number you're looking for is the very last item in a list of n items? Or, actually, what if it's not even in the list at all? The computer is forced to perform n maximum comparisons. So if you've got a list with 1,000,000 unsorted items, that is 1,000,000 individual checks, which, as you can probably guess, is just terrible for efficiency when you're dealing with big data. Because dealing with vast amounts of data absolutely requires speed, programmers had to come up with smarter methods. That brings us to part 3, binary search, or splitting lists. Okay, to really grasp binary search, answer this for me. Where do you search for the word zoology in an English dictionary? You certainly wouldn't start at page 1 and read every single word sequentially, right? That's what a linear search would do. No, you'd instantly flip right to the end of the second half simply because you know the dictionary is already alphabetized. You use the order of the information to completely skip all that unnecessary searching. And that right there is the secret sauce. The big trade-off is that for a binary search to actually work, your data must already be sorted in order, whether that's numerically or alphabetically. You absolutely cannot do a binary search on an unordered list. But if you do take the time to order that list up front, the efficiency you gain when searching is just massive. Here's the exact play-by-play of how it works. First, the computer finds the exact middle position of the sorted list. If the list has an even number of elements, it usually just rounds down. Then, it compares that middle element to the key you're looking for. If your key is greater, well, now we know for a fact the key has to be in the second half. That means we can completely throw away the entire first half of the list. By repeatedly splitting the search area in half, which is why it's called binary, we drastically reduce the number of checks. It literally turns what could be millions of comparisons into just a handful of quick iterations. It's a total game changer. So binary search is incredibly fast. But what if we could do even better? What if we could find our data in exactly one step, no matter how big the database is? Welcome to part 4, Search by Hashing, the one-step shortcut. Hashing is honestly like a magic math shortcut. Instead of searching around, it looks at the data itself to calculate the exact address where that specific piece of data lives. It uses a formula called a hash function. A super common one for numbers is the remainder method. It simply takes the value of your item, divides it by the total size of your storage space, which we call the hash table, and then uses the remainder as the exact index position. Let's visualize this so it clicks. Picture an empty hash table with 10 slots. They're indexed 0 through 9, and they're just waiting to be populated using our remainder shortcut. Right now, every single slot is completely empty, holding a none value. Watch what happens when we want to store the numbers 80, 51, and 34. When we apply our math, dividing by 10 to find the remainder, the number 80 gives us a remainder of 0, so it drops straight into slot 0. 51 gives a remainder of 1, so it pops right into slot 1, and 34 goes straight to slot 4. Now, if we want to search for 34 later on, we do not scan the list. We just run that same quick math. 34 divided by 10 has a remainder of 4. We check slot 4, and boom, it's right there. Instant lookup in exactly one step. Zero searching required. Sounds perfect, right? Almost too good to be true. Well, no system is completely flawless, and hashing brings its own unique headache. Part 5, the collision problem, or handling duplicates. Take the numbers 16 and 26. If we run both of those through our modulo 10 remainder function, they both give us the exact same remainder of 6. This creates what we call a collision. You basically have two different items fighting for the exact same parking spot at index 6. And since a hash table slot can only hold one item at a time, programmers have to build specific collision resolution mechanisms to handle these traffic jams. It definitely adds a bit of complex engineering behind the scenes. So the next time you type a query into your phone and hit search, take a split second to wonder, what algorithm is actually working behind the glass? Whether it's the exhaustive checking of a linear search on a tiny list, the incredibly clever having of a binary search through a massive sorted database, or the instant mathematical magic of hashing, you now understand the invisible architecture that actually retrieves the world's information right at your fingertips. Thanks so much for joining me on this explainer. Keep wondering how things work, and I'll catch you next time.